Hello everyone. Regarding the equation of ideal gas, if we just want to combine these three laws that I talked about them already, I repeat them again here. Boyle's law, Charles' law, and Avogadro's law, which all of them shows the relationship of volume first to the pressure, but inversely to the temperature directly, and to the amount of the gas directly. If we combine these three laws, we can reach the equation of the ideal gas. So what's that? This equation describes the relationship among the four variables: pressure, volume, temperature, and amount of the gas. And an ideal gas is a hypothetical gas whose pressure, volume, temperature, behavior can be completely accounted for by the ideal gas equation. So when you combine these three laws together, so you will reach this equation first: V proportional to NTP, and then you want to convert the proportional sign to equals, you use R, which is the proportionality constant. As I mentioned, R is proportionality constant, and before we can apply the ideal gas equation to a real system, we must evaluate the gas constant. We must evaluate it. So consider that at a standard temperature and pressure, we can write first the gas equation PBNT, and we can say in STP situation we have, it means that in 1 atmosphere an ideal gas occupies 22.440 liter. In a standard atmosphere, at 1 atmosphere, this volume occupied by an ideal gas, and then the number of the mole is 1 mole, and while the temperature is 0 Celsius, which is in Kelvin 273. So when you calculate, R equals to 0.082057, which the units of liter, atmosphere, Kelvin, mole. Let's solve some problems using this equation. Sulfur hexafluoride is a colorless and odorless gas. Due to its lack of chemical reactivity, it is used as an insulator in electronic equipment. Calculate the pressure in atmosphere exerted by 1.82 moles of the gas in a steel vessel of volume 5.43 liter at this temperature. First, we have written all the parameters that this equation provides us in order to find the pressure in atmosphere. We have the equation for the ideal gas, and it is enough just to substitute these amounts to find the pressure. So I will write here, so pressure equals to, where the number of the amount of the gas in mole multiplied by R, which calculated already, 0.0821, with the unit liter, atmosphere, Kelvin, mole, multiply by the temperature. Of course, the temperature in degrees Celsius have to be converted to Kelvin. So we will write it, and we add it to 273 Kelvin in order to change the unit, divided by the volume, the 3 liter. And finally the results is 9.42 atmosphere. And also, regarding another example, ammonia gas is used as a refrigerant in food processing and storage industries. Calculate the volume in liters occupied by 7.40 grams of ammonia at STP. So this example is a little bit different from the previous one, and we need to use a tip, recognizing that 1 mole of an ideal gas occupies this volume that I told you at the beginning of this video at STP, of course, and using the molar mass of ammonia. So we need it. First, we need to find the grams of ammonia and convert it to moles and liters at STP. How we do that? Okay, we write like that. To find the volume, we have the grams, 7.40 grams of ammonia multiplied by, we know 1 mole of ammonia has the molar mass of 70.3 gram of ammonia, and it has been shown that in STP 1 mole of ammonia occupies 22.41 liter of volume. They go, and then finally the result is 9.74 liter. Regarding this new formula, let's focus on me. I have to describe it for you. Consider that we have a gas number 1 here, which is sealed inside of the cylinder at room temperature with a specific pressure and volume. So we have it. Because the ideal gas constant R is always constant, we can isolate it based on the initial conditions. So we can write the ideal gas equation for the gas number 1. After changing, let's focus on number 2. This represents the new conditions of the gas after an external action has modified it. What are they? For example, heating it up, compressing the container, or adding more gas. So changing all these parameters. It is represented by the subscription number 2 that I told you. Since R never changes, again, the new conditions must still equal that same constant. So again, you can write the equation of the ideal gas for this condition as well. Now we can set the two sides equal to each other here. This equation, and write it, I mean write it, because R is constant, you can set it. This equation allows scientists and students to predict exactly how a gas will behave. If you know the initial conditions, for example, for gas number 1, before changes we can say, and you alter a few variables, you can easily calculate what the remaining unknown variable will look like. In some occasion, for make this equation easy, we will consider that the amount of the gas is always 1, and if N1 equals to N2, you can eliminate them from both sides and simplify this equation like that.